All right, welcome back everyone. This is the third video in our third playlist for Kalman filter theory and applications. We're dealing with state space concepts. So let's get to it. These are the main playlists that we have. We're working on this third playlist. And as we saw before in the last video, these are our topics that we're going to be dealing with in this playlist. We're now on the third video, which is going to show examples of differential equations and how they can, how state space models can be derived from them. Okay, the simple harmonic oscillator we've seen before in earlier playlists. To convert this to a state space form is very simple. We just define the output variable y to be the state variable x1, and then x2 is the derivative of x1. And then we rewrite the equation as we do in the last line there. That gives us a vector matrix form looking like this. So the state vector is x1, x2. Its derivative with respect to time is on the left, and then the matrix, the companion matrix, is shown there in the bottom. So recall that a single nth order ordinary differential equation represents one, but only one way of deriving a state space representation. You can also derive state space models directly from systems of coupled ODEs. So they have some state variables that couple the different differential equations together. We'll take a look at that in a minute with a coupled harmonic oscillator system. You can also convert such ODEs, coupled ODEs, into a single nth order ODE if you want, a fourth order equation for two second order systems, for example. And systems consisting of electrical, mechanical, thermal, hydraulic components are typically coupled in this way. For example, a DC motor driving an inertial load, which is an example we'll be looking at shortly. If you're in dealing with the discrete time representation, then ordinary difference equations can yield state space models, and we'll take a look at that in the next video. And of course, you can derive models empirically using system identification techniques, which will not be the subject of this particular playlist, but we will deal with that in later playlists. Okay, so let's take a look at a coupled ODE consisting of two damped harmonic oscillators. They are connected by a third spring. That's the coupling device. These are our coefficients and spring constants and damping coefficients. We've got two masses connected by a coupling spring, and we have a schematic diagram of this in the next slide. Here it is. So we're measuring the x position along the x-axis of the masses M1 and M2. Each of those masses is connected to a wall, an immovable wall by springs, and also by a dash pot or a damping device. The two different masses are also coupled together by a third spring, and that's K3. That provides the physical coupling for the system. Okay, so defining the states, we can say let x1 be the displacement of mass m1 from the equilibrium position. x2 is the displacement of the mass m2, and then we have the velocity of those items as well. Notice that we could have presented these in a different order. We could have said x1 is the displacement of m1 and x2 is the velocity of m1, and just kept the two state variables for each of the subsystems together, but it doesn't really matter. It's equivalent. The matrices are similar. So here are the state space equations that result. Won't go into the derivation of this from the first principles, but you can see how it kind of makes sense. The first two equations are essentially just definitions of the x3 and x4 variables with respect to the derivatives of the first two variables. And then once you take the derivative of the third and fourth variables with respect to time, then Hooke's law kicks in and all the internal coupling and the mutual coupling via the K3 spring constant show up. So you can see the difference here in a minus sign on K3 for X3 and a plus sign of K3 for X4 that indicates that one of the masses is going to be moving to the right while the other one's moving to the left and so forth. They kind of have an opposite pull on each other. All right. So in state space form, it's very simple to write the companion matrix. The first two rows are the definitions, the rows that provide the definitions of the variables. So you can see it's zeros except for a 1 in the third column for x1, because x1, the derivative of x1 is by definition x3, and the derivative of x2 is by definition x4. So we have a plot of the Python simulation in the next slide. All right, you can see here that we have x1 and x2, which are the displacement of the masses. The first mass is shown as being close to the equilibrium point. Okay, it's to the left of the equilibrium point. That's x2. And x1 is shown to the right of the equilibrium point here for initial conditions. And what you see is that the x1 mass tends to dampen a little bit more slowly than the x2 mass. You can see that the dash pot must be a little stronger on the second mass. It's slowing down here over time. And you'll notice in the velocities that the blue lines are phase shifted from each other 180 degrees, which is what you would expect for velocity versus displacement. And the same sort of damping pattern is available here. All right, for our next model, we're going to take a look at a DC mode our DC motor with an inertial load. It's an electromechanical system. Here's the inertial load on the right. It's a mass, so it's governed by Newton's laws, mechanics, and friction, and so forth. Then we have a DC motor, an armature with wound coils inside of magnets to make a DC motor. Represent the inductance of the motor with L and this symbol here, and the resistance over here on the left with the symbol R. And then we have an applied voltage. Now coming back from the motor is a back EMF, sort of a response of the motor, because the motor is both a motor and a generator, if you will. It's moving through an electromagnetic field, so it's going to generate this back EMF. And we'll talk about that a little more in a second. So that's the diagram. What are the variables? Okay, so R is the motor resistance, L is the motor inductance, theta is the rotational position of the load, how much you've rotated the load by angularly, and its rate of rotation is omega. Then we have a frictional constant, a torque that's applied to the load. We also have an armature constant, which is based on the number of windings of on the armature. And then there's the applied voltage from the battery or some other source that would be applied. And then the back EMF coming out of the motor, generated by the motor, and the constant for that back EMF. So let's talk a little bit about back EMF. This might not be familiar to some of you. So it's based on electromagnetic induction and rotational motion. So the changing magnetic field induces an EMF in the windings. And this is governed by Faraday's law of electromagnetic induction. The rotational motion, however, rotates the armature within a magnetic field, and so the windings also cut through magnetic field lines. So this kind of force that's generated from that rotation is in opposition to the applied voltage. So the back EMF acts against the applied voltage, and it's proportional to the speed of the motor. So if you look at the rotational rate of the motor times the back EMF constant, you'll get the back EMF voltage. Why does this work that way? Well, it's basically the motor-generator duality, if you will. A motor converts electrical energy into mechanical energy, and a generator converts mechanical energy into electric energy. And the conservation of energy says that they have to balance each other. And so that's what the back EMF essentially does. It ensures that the energy supplied by the battery is going to be balanced out by the back EMF. The back EMF can actually be used as a control device. It's a sort of a feedback, if you will, and a higher speed increases the back EMF, and that reduces the overall net voltage. So you can use that to help regulate the speed. All right. So just summarizing what back EMF is, it's due to electromagnetic induction. It acts in opposition to the applied voltage, provides a natural speed regulation, and ensures energy conservation. And it's basically due to the fact that a motor is also a generator. Okay, let's move on. Talk about the state space model. Okay, so here are the governing equations. We won't derive these from first principles. You can take them as given. Some of them will be familiar to you. So the rate of change of the rotational position is omega. That's your basic definition of omega. Then we have the applied voltage minus the back EMF minus the resistance times the current going through the resistor or the resistance. That gives you the inductance times the rate of change of current. And then J is the moment of inertia times the rotational acceleration. So this is like an MA, right? F equals MA, so that's like M, moment of inertia, and a rotational version of acceleration, if you will. That's equal to the applied torque minus the force that comes back from the rotation itself. The resistance, if you will, to the rotation, the frictional force. Then there's the back EMF force that we talked about before. So given those four equations, and here's the definitions which I just mentioned, we can derive a state space model from those equations. And it looks like this. Here we have omega being defined in terms of theta as the derivative of theta, and then the other equations that we had for connecting the different, the current rate of change of current and the rotational acceleration to I and to omega. We also have an input term here. Okay, if you have an applied voltage, that's what it would be. If you had an applied voltage that was going for a while and you just shut it off, became zero, then you just have a perfect dynamical system that was coasting. Basically, friction would slow it down, just like the dash pot slowed down the harmonic oscillator in the previous slides. Okay, now we'll take a look at what these values look like for a nominal applied voltage. So you can see that you apply a voltage of 1 volt, and you've got the position of the inertial load changing. It's rotating with time over 5 seconds here. And then the current ramps from 0, ramps up fairly quickly. So you have this transient period where the position is not linear. It starts off at 0, and then it's rotating slowly and then more quickly, and then it comes to more of a steady state once the current and the angular velocity have achieved a steady state. Okay, so now we're going to take a look at another model, a predator-prey model. Now, this one is not a linear model, so we won't actually have a state space representation, but we'll give some indication of how you would go about it. But I did want to get you familiar with this particular type of model. So we make some assumptions about the predators and the prey. You can read these at your leisure. Just usual assumptions to make the modeling simplistic and more tractable from a mathematical point of view. And then we get the famous coupled differential equation model called the Lotka-Volterra predator-prey model. This says that the rate of change of the rabbit population is equal to the rate of reproduction, if you will, of the rabbits. That's the current population times their reproduction rate, minus the death rate due to predation from the wolves. And that is it's a constant CRW times the product of R and W. So the product is the is a product of the population numbers of the rabbits and the wolves. This tells us that this equation is not linear because of this product term. Okay, and similarly, the wolves will grow if they have enough rabbits to eat, and so how quickly they can eat efficiently, they can convert the rabbits into wolves by eating them, and their natural death rate. Since in this particular model, we're assuming that the wolves have no predators, they have a natural death rate. They just live so long, assuming they have food. But if they don't have enough food, they're going to die out sooner. So that's why it's a function not only of how many wolves there are, but also how many rabbits there are. So this is their conversion efficiency, if you will. So those coefficients are mentioned down here. You see CRW is the predation rate, represents the rate at which predators capture and consume their prey. And then the conversion efficiency is how efficiency with which the consumed prey are converted into new predators. So they can reproduce if they're healthy and they have food to eat. And then the natural predator death rate is DW. Okay, so this model in its current form cannot be expressed as a state space model due to its state variable product terms RW in each equation. Later, we will linearize it about its nominal critical values or equilibrium values and show you how you can make a state space model once you do that. However, even though it's nonlinear, its behavior can be simulated using Python, and that's what we do in this next slide. And you can see how it works here. We're assuming somewhat less than 10 wolves to begin with and say 40 rabbits. And as the wolves increase, as they reproduce, they start eating the rabbits, so their numbers come down. But eventually the rabbit numbers come down so much that the wolves start starving. They can't continue to reproduce, they starve, and so their numbers come down, in which case then the rabbits take over, can multiply again. They multiply like rabbits, and this cyclical phenomenon goes on. All right, another nonlinear example is satellite orbits, orbital mechanics. Here we have a simplified model of a circular orbit. This might have as many as 6 terms in the state vector. The dynamics of the satellite are governed by the defining equations. Okay, so here you have the derivatives. And also by the gravitational equations according to Newton's law of gravity. The rate of change of the velocities are dependent on the gravitational constant, the mass of the attracting body, and the cube of the distance from the center of the Earth. And that is true for each variable. Okay, the mass of the planet. I shouldn't say Earth because Earth is not a perfectly spherical body. It's an oblate spheroid. But here's where the nonlinearity creeps in. R is the square root of the sum of the squares of the x terms, so that's a highly nonlinear item. So we're not dealing yet with nonlinear equations. As I mentioned before, to create a state space model, you have to first linearize the model about an equilibrium point, and then you can use a linearized model in an extended Kalman filter, which we'll get to. Okay, once you've linearized the system, you can identify the states in the usual way, but you kind of know what the states are. We just can't express the state equations yet until we have linearized them. Can't express it in a linear matrix form. Okay, so where are we at? We've considered several physical examples: simple harmonic oscillator, coupled harmonic oscillator, predator-prey system, which was slightly nonlinear, and then orbital dynamics, which was even more nonlinear. We've also looked at the electromechanical system, which is still linear. Okay, so often we get these states from the primitive physical variables and their derivatives, and by coupling states due to the underlying physical interconnection models. and of course the physical laws that govern the individual parts. All right. So nonlinear differential equations do require more work before a state space model can be constructed, and eventually we'll get to that. But in the next video, we're going to take a look at ordinary difference equations. And then as a reminder, we have our Python scripts out on GitHub. So that's it for today's video. We thank you for watching, and we'll see you in the next.